So we'll go ahead and get this out of the way here. So yesterday I taught you guys how to solve systems of equations with a matrix, right? We learned about the row operations and how to use the row operations to turn a matrix into what we call the reduced matrix. And so in the examples we saw yesterday, we always got exactly one solution for a system of equations, and that'll happen a lot, and that's good. But as we know from before when we talked about just systems of equations in general, sometimes you'll get maybe no solutions or you'll get infinitely many solutions, right? Those are our three possibilities. And so that's still going to happen here when we're dealing with systems of equations with matrices. And we just want to see how to deal with those with a matrix. What's it going to look like with a matrix? How will I know by looking at a matrix if there's no solutions or if there's really many solutions? So I want to do a couple of examples to illustrate those today and how to deal with those. So here's our first example. I'm going to give you this system, and this will double as a refresher of stuff I talked about yesterday. So all right, so here's a system of two equations. Okay, we're going to go ahead and solve it with a matrix using the matrix method, and we're just going to see what happens. So the first step always when we're using matrix methods is let's write down the augmented matrix for the system. So we'll go ahead and do that. Just fill in the numbers. I get 1, -2, 0, and I get -3, 6, 3. Okay. So now I have my matrix. Let's run the algorithm. Let's reduce this matrix. Yeah. Okay, so the first thing was I'm supposed to get a leading 1 here. Oh, that's already a 1, so that's good. First step is complete. I have a 1 there. The next thing I would need to do is get a 0 in the column underneath it. So I need to make this -3 into a 0. How do I do that? Well, what cancels out -3? How about +3? We'll multiply this first row by 3 and add it to the second row. So we're going to add 3 times the first row to the second row. So row 2 plus 3 times row 1. Yeah, we'll add 3 times the first row to the second row. Okay, so what happens? Well, that's going to be -3 plus 1 times 3. That's -3 plus 3 is 0. I'm going to get 6 plus 3 times -2. That's 6 plus -6. That's 0. I'm going to have 3 plus 3 times 0. That's 3 plus 0. That's just 3. And then I don't change the first row. So here's my new matrix. Okay. This looks a little funky. What do we do with this? Well, technically, if I just kind of ignore over here, this coefficient matrix over here is reduced. This is actually reduced. I have a leading 1 here in this row. And then remember, one of the stipulations is just that every row has either a leading 1 or it's all zeros. So if I kind of ignore this, here I have a leading 1 in this row. And in this row, I have all zeros. So it looks like this is a reduced matrix. So I'm supposed to be able to find the solution from this, but what's wrong? Let me grab another color here. What's wrong is if we look at the second row, look at that second row. If I tried to turn this matrix back into a system of equations, what am I going to get? I'm going to get x minus 2y equals 0 for the first row. And the second row is going to tell me, well, 0 equals 3. So this kind of thing should look familiar when we had our discussion of no solutions for a system of equations. Whenever I get something like this, that's just false. So it's definitely false. That means that there are no solutions. So there are no solutions at all to this system of equations. How do we identify that from the matrix? Well, exactly like this. If you ever run into a bunch of zeros to the left of the bar, and then something that's not 0 to the right of the bar, that means there are no solutions. So if you have a row that looks like this, that means there are no solutions. You can just stop and say no solutions. Okay. Need my eraser. So here's an example of no solutions. Again, the sign is, the sign that you have no solutions is that you have zeros to the left of the bar and a non-zero thing to the right of the bar. Okay. Your book might call this a contradiction. It's maybe a word you would hear. Maybe I'll use that word sometimes. I don't know. Anyway, if you run into a contradiction like this, applying that, means there's no solution. Okay. And if you ever encounter one of these on an exam or an activity or something, just say no solutions. Yeah, you don't have to get fancy. Just write that. Okay. So there's an example of no solutions. Let me do another example, and we'll sort of summarize everything. Okay, here's a new example. This one will be a bit bigger. We're going to have x minus 2y minus z equals 1. We're going to have 2x minus 3y minus 2z equals 5. And we're going to have negative x plus 2y plus z equals negative 1. Okay. So here's a new system of equations. This one has 3 equations and 3 variables. Okay. So again, we'd like to solve this thing. And again, I'm going to insist that we use a matrix to solve this. So let's go ahead and just write down the matrix first. Yeah. Write down our augmented matrix. That's always the first step. So just read off the numbers. The first row is 1, negative 2, negative 1, 1. The next row is 2, negative 3, negative 2, 5. And the third row is negative 1, 2, 1, negative 1. Okay, so here's our augmented matrix. And now we're just going to solve it and see what happens again. We're going to run the algorithm. So the first thing I need is, of course, I have the leading one here already, so that step is complete for me. I already have a leading one here. So now I need to make these guys into zeros. Yeah, I need that 2 and negative 1 to be 0. I got to make zeros everywhere else in the column. So to do that, I can do that in 2 steps. What will cancel 2? Negative 2 will cancel 2. So let's multiply the first row by negative 2 and add it to the second row. So we'll do row 2 plus negative 2, row 1. Okay. So what happens to the second row? Well, this will be 2 plus negative 2, that's 0. Negative 3 plus, so negative 2 times negative 2 is positive 4, so that's negative 3 plus 4, which is positive 1. Negative 2 plus negative 1 times negative 2, so negative 1 times negative 2 is positive 2. So negative 2 plus 2 is 0. That's my bar. And then it'll be 5 plus negative 2, which is 3. Okay. So here's my new second row, and then I haven't changed anything else. Okay. Now I still need to make a 0 here. So I'm not done with the first column yet. I still need to make a 0 here, according to the algorithm. So let's go ahead and do that. And I just need to cancel negative 1. Well, 1 will do that. So I actually don't need to multiply this row by anything. I can just add it to here. So we're just going to do row 2 plus row 1. And what happens? Well, negative 1 plus 1 is 0. 2 plus negative 2 is 0. 1 plus negative 1 is 0. And negative 1 plus 1 is 0. Okay. And we'll fill in the rest. We didn't change anything else. Okay. So that's a little suspicious. I have a row of all zeros, including to the right of the bar. Everything is 0. You know, if I translated this row into an equation, it would tell me 0 equals 0, which sounds like something that's always true. 0 is definitely equal to 0. Okay. Just to be a little nitpicky, we're not done reducing this matrix yet. This is not reduced. If you take a look at this matrix, you'll notice I have a leading one here, and this one is all zeros. But this row doesn't have a leading one yet. I have a 1 here, but it's not leading because there's something non-zero in its column. So the next thing I would do according to the algorithm is move over to this column, the second column, and try to get a 0 up here. I need to get a 0 where that negative 2 is. So to finish this off, let's just get a 0 there. And then we'll discuss the result. So I'll leave that matrix down there. But we'll kind of loop back around on the board, if you will. So this is going to, I don't know. Maybe I should just rewrite the matrix quick. so it's a little less confusing on the board. Okay, so this is our matrix. Again, I'm looking for a 0 here. So how am I going to get that? Well, I'm going to use this leading one to kill this -2. So to cancel out -2, I need to add +2. So let's multiply the second row by +2. So row 1 plus 2, row 2. And that should cancel that out. So what do I get? Well, 1 plus 2 times 0 is just 1 plus 0, so I still get 1. -2 plus 2 is, of course, 0. -1 plus 0 is -1. And 1 plus 2 times 3, well, that's 2 times 3 is 6, so it's 1 plus 6. That's 7. And I didn't change anything else. Okay. This is now a reduced matrix. I've got a leading one in this row, a leading one in this row, and these are all 0. So this is a reduced matrix. So we're basically done. So now we just need to interpret this result. And there's sort of not an issue, but there's just something subtle that we have to deal with, which is, what are my solutions? You know, if I try to turn this into a system of equations, what do I get? I'm going to get, from this first row, I'll get x minus z, because there's no y term. The y column has a 0, is equal to 7. And the second row would tell me y equals 3. Yeah. So I'd have x minus z equals 7 and y equals 3. That would be this matrix. And if I want to, this last row would tell me that 0 equals 0. Yeah. Okay. So what's the problem here? Not the problem, but what's going on? If we look at these equations, I know y is equal to 3. So I have a value for y. That's good. I want that. But if I look at this first equation, I have x minus z equals 7. I have x and I have z. I have no way of getting x equals number or z equals a number, because these guys are both in one equation together, and I have no way of separating them really, right? I have this last equation that's useless. I already know 0 equals 0. This doesn't help. So I have no way of substituting an x for a z or something so that I could solve for x or anything. I'm kind of just trapped with both x and z in this equation, and there's nothing I can do about it. That's not so bad, and the consequence of this is that there are infinitely many solutions. So I'm going to write over here, there's infinitely many solutions. But it's nicer than that, than just saying there's infinitely many. I can actually tell you what the solutions have to look like based off these equations that I get from the matrix. I can tell you what the solutions sort of have to look like. What do I mean? I'm going to introduce a bit of terminology for you guys. So let me just write a word here. We'll do it up here in the corner. Should invest in a larger board. Let's see. So this is our final matrix. Let me give you another definition here. Some terminology that we'll use. And this will show up on activity 5.3b. So an arbitrary parameter, a variable is an arbitrary parameter. So the word I'm defining here is arbitrary parameter. This is what your book calls these. An arbitrary parameter, if its column does not have a leading one in it. So when I look in a reduced matrix, remember that each column represents a variable, to the left of the bar anyway. Each column represents a variable. And if the column representing of some variable does not have a leading one, then that variable is what we call an arbitrary parameter. And in a second, I'll make clear why we give it this name. But it's an arbitrary parameter. So if we look over here, what is the arbitrary parameter? Which column is missing a leading one in this matrix? Well, if we look, I have a leading one here. Everything else is 0 in this column, and there's nothing to the left of it. This is also a leading one because it's the only non-zero thing in its column, and everything to the left of it in its row is also 0. So this is a leading one. So the only possibility is that this last column, this third column, this has no leading one in it. There's this -1 up here. It's not a 1 in the first place, and also it's not leading because